Hello, welcome for the second talk of the Infinity workshop today. The speaker now is Henry Sinclair-Banks. He did his PhD in the University of Warwick and then had a postdoc, I think, in Warsaw, and now he's moving to NPI. If you want to get passionate about vector addition systems, just talk to Henry for 5 minutes. And with no further ado, Henry, the floor is yours.
Thank you. Thank you for the introduction, and a wonderful audience. Thank you for choosing to attend my talk. Hopefully Radek's right. Hopefully you'll get excited about vector addition systems, which I'll define in a moment. And you might be a little bit suspicious if you read precise, right? I thought this was about fine-grained complexity. About 80% of what I'm going to talk about is fine-grained complexity, and about 15% isn't, and then there's going to be 5% of open problem at the end. So yeah. Without further ado, vector addition systems with states. So I kind of got a feeling that most people here are kind of track B-ish autometry, but there's a few people who aren't. I'm going to present this as if you're all in track A for the sake of warming everyone up at the same speed. So I give you a directed graph, and I put integer vector labels on the graph. Here I've got two-dimensional integer vector labels, hence two-dimensional vector addition system with states. And to be clear about the language, you might call these nodes, I'll call them states, and you might call these edges, I'll call them transitions. I might also call them edges and nodes, so bear with me. And this is such a mouthful that I'll shorten it down to 2 VASS, or if I have 3 dimensions, it'll be 3 VASS, if I have 4, it'll be 4 VASS, etc. And an important point here is that we'll take walks through these graphs as you would expect, and as I go, I'll be adding the vector labels one by one. And as I go, I must make sure that my prefix sum, which can be thought of as a counter value, must remain non-negative all the time. So imagine I'm at node A, or state A, and I have 0, 0 on my 2 counters. I cannot transition up to C because I'd go negative actually on both counters, but I can transition down to B and I'd go to the configuration 2, 0. So to be clear, the counters store natural numbers, but the updates are integers. I hope that's really clear. And this presentation is concerned with a problem called coverability, my favorite problem, and hopefully you'll enjoy it, which asks the following. I give you as input a vector addition system with some number of counters, an initial configuration, which is some starting node and some starting counter values. You can imagine them starting with 0 for the sake of your understanding. And some target, which would be some other node, and you could also target also with 0 counter values. And the question I care about is a state reachability question. I want to know whether you can get from the initial configuration to the target node with at least the counter values that I specified in the target. So here's an example. Can I get from A starting with 0, 0 to G with at least 0, 0? So basically, can I just reach node G? I didn't realize the size of the slide to the size of the root, so it might be a little bit difficult, so we'll go through this one quickly. As we already saw, you can't go up to C, so we'll go down to B. We'll go up to C now with 5, 8, along to E with 3, 10, down to D with 7, 5. And now the issue, right? This is where VASS really show their complexity. I can't go to G directly, right? If I take the top branch via F, I'd go negative on the first counter. And if I took the bottom branch, D, directly to G, then I'd go negative on the second, right? So I scratch my head, I'm like, oh, where do I go? But then you notice this cycle, which has +1 on the first counter and +10 on the second counter. And VASS have this lovely monotonicity property, which is if you can take a cycle, then you can take it over and over again after you've taken it one time. So now I can get both counters as large as I want. I only need to take the cycle 2 times. I get to 925, and then I can zip over to G and get there with at least 0, 0. I hope the problem makes sense. And before I talk about actually interesting things, I'm going to fix 2 terms. So remember these for the rest of the talk. This is the one thing I ask of you today. D is the dimensions, the number of counters, and N is the size of the instance. I'm going to have size of instance encoded in unary, so that'll be number of nodes, number of transitions, the one norm of every vector, maybe the one norm of the target, and the one norm of the source. Okay? And so now you can see the rest of the presentation. And it's going to be split into 3 parts. In part 1, I'm going to talk about general VASS with arbitrary dimension, denoted dVASS. Here, I'll talk briefly a little bit about the history about what the complexity of coverability is. And I'll talk about a fine-grained lower bound that we have a conditionally optimal algorithm in terms of the time required to solve coverability. And I'll talk about the reduction because it's really nice. I think the idea is juicy. It's a parameterized reduction from K-clique detection. In part 2, I'm going to drop a load of counters and go to 2 VASS. in which the problem becomes much simpler. You can solve coverability in polynomial time, we'll get there later, and I'll talk about another fine-grained lower bound, this time from detecting whether a directed graph contains a K cycle. And then in part 3, I'll talk about one VASS, right? Makes sense. Here I'll touch briefly on the fine-grained complexity. This is the precise bit. I'll talk about the state of the art, a very basic algorithm that runs in quadratic time, and then the ideas behind an AC1 upper bound. So this is not the fine-grained complexity, but rather the circuit complexity. And then I'll talk about an open problem I think is interesting. We'll get there in due course. So the complexity of coverability in general. There's this theorem that we got a few years ago that's really based on Rakoff's idea, which is a famous result that I hope a few of you here have heard, which is the following. I'm not going to talk about it too much, but I have to start here, which is that if coverability is positive, right, so from Sx you can get to t at least y, right, so if coverability holds, then there is a run that's short enough. When I say short enough, it's double exponential, n to the power of 2 to the power of a constant times d. The constant hidden by this O is actually not so bad. The reason there's 2 citations here is that Rakoff had n to d, and we have n to 2 to d. And this immediately yields a double exponential time algorithm for solving coverability. Here's how it goes. It's a hilariously simple algorithm. Given that you know coverability can always be witnessed by runs of length n to 2 to d, that means the maximum counter value you could ever possibly observe on this run is n to 2 to d times the maximum update that a counter can receive. Well, and that's obviously bounded by n, so this is basically n to 2 to d. And now imagine the configuration space of n to 2 to d counter value bounded configurations. Right, so it's a double exponential directed graph, and now imagine implicitly exploring this with your favorite graph searching algorithm like BFS or DFS, and this will terminate in time n to 2 to d. Right, so the algorithm is really simple, but its proof of correctness is hidden behind the theorem. And on the other side, and this is kind of where we're going to talk about more, there are instances of coverability that really require long runs. So Lipton proved in 1976 that coverability in DVAS, although there are a family of instances that require n to 2 to constant times d. Again, the constant hidden by this omega here is not that bad. I think it's something like 1/8 or 1/16. So these are fairly sharp. To give you a flavor, I'm going to give you an exponential example. So here's a warm-up into the rest of the talk. Imagine you want to get to Q, and I don't care what you're covering, let's say Q0000. In order to get there, so we're going to work on this one backwards, you have to get at least 1 on the 4th counter. To get at least 1 on the 4th counter, you have to take this cycle once, which means you have to have at least 2 on the 3rd counter, which means you have to take this cycle at least twice. And take this cycle at least twice, you have to take this cycle at least 4 times. And take this cycle at least 4 times, you have to take this at least 8 times. You can imagine building this up, and this will prove that any run that witnesses coverability in an example like this is exponential in the dimension, roughly 2 to the power of d. Lipton's result is significantly more powerful, and you would like to conclude, this is a fake theorem, that coverability in DVAS requires n to 2 to d time, right? To be like, oh, this is optimal, this Rakoff algorithm, or Rakoff-based algorithm is as good as you can get, but, ooh, oh no. But unfortunately, this implication is not there yet. And actually, we don't know this theorem. This is just not a theorem. We really don't know. But we have the next best thing, which is that conditionally, one requires n to 2 to d time to decide coverability. And we have this under the exponential time hypothesis. Thanks for Henning's amazing introduction talk. I don't need to talk about the exponential time hypothesis very much. I've given the very informal flavor that SAT with k variables requires 2 to the k time, very roughly speaking. But I don't want to work with SAT. Instead, I want to work with clique detection. And there's this result that under ETH, detecting whether an n-vertex graph contains a k clique requires at least n to k time, roughly speaking. And I want an even more precise statement. I want k par-type. So I'm going to split my vertex set into k subsets, and I want my clique to have 1 node in each vertex subset. And we're going to use this result in the following. We're going to devise a parameterized reduction to coverability. Right? It might sound a bit suspicious at the moment. I'm going to somehow detect cliques with the counter machines that I showed you earlier. I'll go through it all slowly. I think there's some nice pieces that we're going to build together. And we're going to, it's parameterized because we're looking for a 2-2D clique in a 2-2D par-type n-vertex graph And if you kind of stare at it for a moment, right, this is the K for your K clique problem. You shove it in here and you get an N to omega of 2 to D, right? Which is kind of looking like a white flavor. We'll wrap this up later. But to go through this, there are 2 steps. And in the middle, I'm going to need bounded 2 counter machines. What's a 2 counter machine is a reasonable question. But let me just give you the proof idea. The 2 steps are first, I'm going to do clique detection in bounded 2 counter machines, and then I'm going to take bounded 2 counter machines and simulate them with VASS, like directly, and obtain the result we want. A bounded 2 counter machine is kind of like a VASS, but there's two differences. One is pretty obvious. It's got a bound. So the counters are between 0 and n to 2 to d. And the other addition is that I can take 0 tests. So to be precise, let's stare at this example for a while, right? I can either write them as counter programs like this, or I can draw them as finite state machine graphs like this, right? So what happens here? Imagine I start with x on counter x and 0 on counter y. The first loop pours x into y, right? Like I decrement x by 1 and I increment y by 1. And then I'm asked to test x for 0. So to be really clear about what this transition means, it means I can transition from one node to the next only when this counter is 0. So this basically forces me to pour the whole of x's value into y. And so after this 0 test, I know that x is 0 and y has value x, as it had to begin with. And then I'm forced to do the same back, but when I do the same back, I take the value of y and I pour it into x at the rate of 5 times as much. So this then is forced to complete, and I know that if I started with x 0, I must come out with 5x 0. So we're going to call this guy multiply x by 5. Makes sense. Now that I've shown you this, I don't need to draw it over and over again, and I'll use this gadget later. I can also modify this to do division, right? So instead of pouring 1 to 1 to begin with, I could take 8 from x, give 1 to y, pour it all the way over, and then pour it back, and this will divide x by 8. And to be precise, this will only be able to pass the first 0 test if x was divisible by 8, which is really nice. And so we're going to be able to combine these 2 gadgets to do divisibility testing. So if I want to test whether a counter is divisible by 5, I first try to divide it by 5, and if I'm successful, then I multiply it back by 5. This will come in just a moment. So the most interesting bit, how am I going to detect cliques? And I'm going to use these divisibility tests that I just spoke about. So I'm going to start with a k-part type n-vertex graph. Here's what I prepared earlier. And I'm going to associate the first n primes with the vertices, right, one by one. This is somewhat reminiscent of the Stockmayer-Mayer 73 paper that Henning spoke about, but it's a little bit different. The encoding I'm going for is slightly different. And a candidate k-clique will be represented as a product of k primes. This is the difference. We're not going to use Chinese remainder encoding. We're going to product these things together. And so suppose I just choose these guys, right? I choose the node number 2, 7, 13, 23, I don't know, maybe there's some others. How do I test that this corresponds to a clique with divisibility? Well, what I'd like to do is for every vertex subset, let's say v1 and v2 for sake of conversation, to be able to find an edge between them, whose endpoints, right, the 2 primes, I can test divisibility against this combined value c. And if I succeed, then I know that for this edge, I must have selected its 2 endpoints in my encoding. And if I can repeat this for every vertex subset, then I would hopefully test that I have a k-clique. So to go through this example, between vertex set 1 and 2, suppose I have this edge, right, between 2 and 7, then clearly by testing c is divisible by 2 and 7 at the same time, then I know that this edge will be kind of covered by my choice of clique. And I can repeat this over and over again for every single edge, right? So I'll do this k choose 2 many times, one for each pair of vertex subsets, vi, vj. And so the formal statement, which I realize is probably not super readable, I'd like to shove this up, is that there exists primes, right? I can choose one node in v1, one node in v2, etc. Take their primes, such that for every pair ij of vertex subsets, vi, vj, there is an edge between them, right? So vi cross vj intersect the edge set. There really is an edge with endpoints p and q, such that p and q divide my big product of primes that I chose as my candidate clique. And I claim that this is all we need to decide whether there's a k-clique. I hope that makes sense. Cool. So, bring the correctness up. I'm just going to have to insert just a tiny little bit of automata capability, right? I'm going to show you a tiny gadget with guessing with non-deterministic branching. This is extremely simple, and I'm going to use it, but the next slide is fairly compact, so I'm having to just sort of compress this. I can obviously do branching counter machines, right? I can have a node that has 2 transitions out that you can choose between. So if I, let's say, have a machine like this, right, that literally adds just a constant 1, 2, or 3 to x, and I want to say that the precondition is x, and afterwards either x plus 1, x plus 2, x plus 3, I'm going to call this guess, right? It's nothing special, it's just non-deterministic branching. It looks like this, right? As you would expect. So when I write down the word guess, you should have this kind of picture in your mind. So the first part is that I need to guess a candidate clique. I'm going to do this in 2 phases. First, guess a clique, and second, verify that my guess is really a clique, right? And so for this, I want to multiply by each of the primes, and I'll let you choose, right? So for V1, I'll let you choose the prime. For V2, I'll let you choose the next one. If I start with 1, 0, and I use that multiply gadget that you've definitely forgotten, then I can multiply 1 by P1, and then by P2, and then by P3, all the way up to Pk. So after k many copies of choosing a prime multiply and choosing a prime multiply, at the end, I'll have any choice of possible k clique, but now I need to check the edges are there. And like I said, for this, I take a vertex subset, let's say V1, V2, and I guess an edge between V1 and V2, let's say P1, P2, right at the 2 endpoints, and then in order to check divisibility, right, that my edge really is selected by these 2 nodes, then I need to divide x by P1, P2, and then multiply it back, right? I can only pass the divide if I was divisible by P1, P2, and then later I probably want to do some more divisibility checking, so I multiply back, so you can later check this. I do this for every possible pair VI, VJ. So there's like k choose too many copies of this gadget. And I'll get to the end with exactly the counter values I started with, only if I was able to succeed all these divisibility tests. And so I can slam on the sticker of correctness, right? But this counter program terminates if and only if there was a k clique, which is good. And so now I need to tell you how to simulate these machines with VASS. I'm going to black box something.
Oh no.
Oh no. Oh, come on.
Spoilers.
Yeah, you got a lot of spoilers. You've seen all the... Right, that's the end of the presentation, thank you. Did you get it? Okay, so in order to use the simulation lemma that I'll put in front of you in a minute, I need to bound the maximum counter value, and I need to also work out the size of the machine that I just defined, right? Like I gave you this, and it was all compressed because I used gadgets. What's the worst counter value you see? Well, it's a product of k primes. If I let p max be the biggest prime, right, the nth prime, this is something like p to the power of k, right, because I was multiplying together k primes. And this is less than n log n to the k. I'm going to be lazy, less than n to the 2k. And the size of the machine, you just got to trust me on this one. Something like n to the 11. Inside of the divisibility checks, right, I was doing multiply and divide, and I was doing this by a product of 2 primes. So this is something like n to the 4 operations, and I've got k choose 2 of them, so there's already n to the 8 there, and that was the first half. Trust me, it's polynomial, everything's fine. And there's this lovely lemma, an amazing lemma from actually a really interesting paper in my opinion. It's probably the first time people did like kind of fine-grained stuff in VASS as far as I'm aware. In 1985, there's this beautiful parameterized analysis of coverability and boundedness in VASS by Rosier and Yen, and they have this really useful lemma. Now, when I said earlier that Lipton doesn't directly apply the theorem you want, they're using Lipton. Lipton does come up in this. These heavy constructions for simulation are useful, but it's hidden here. It'd be far too complicated to show you. They have the following. In polynomial time, one can construct a VASS with log k many counters that can simulate an n to k bounded 2-counter machine that's polynomial size. This is very efficient, right? I've got an exponential k, and I'm simulating this with log many counters. So you kind of see maybe there's a double exponential relationship, right? This is looking really good for me. You should get excited at this point, like me. And so if we set k equals 2 to d, we got a polynomial size 2-counter machine for detecting 2 to the k cliques. And that thing, right, I said was n to the 2k bounded. And so if I have k as 2 to the d, this is n to the 2 times 2 to the d, say n to the 2 to the d plus 1, bounded 2-counter machine. And I can shove it into Rosier and Yen's lemma, and I obtain in polynomial time something like a constant times d many count of VASS that can detect to the d cliques. So unfortunately, a lot of the magic is hiding behind this beautiful lemma. But I hope this makes sense. And just to be really clear, right, if you remember the sticker of correctness, which says this counter machine terminates if and only if there is a k clique. This is basically coverability. All I care about was that counter machine getting to the very final instruction. That's like asking it, can I get to this control state with any counter value? So it's like coverability to at least 0 on every counter. I really genuinely do not care about the final counter values. So I kind of saying that termination is coverability, right, for the sake of this reduction. And so just to kind of bring everything together, just to sort of piece it all, right, you've seen all the pieces. So detecting a 2 to the d clique in an n-vertex graph requires something like n to 2 to d time under ETH. And then with this product of prime encoding and divisibility testing, I can construct an instance of coverability termination, whatever you want to call it, in a polynomial size, n to 2 to d bounded to counter machine, and then with Rosser-Lenz simulation lemma, I get out a basically d-VASS for which coverability implies cliques, hence the theorem. I hope that makes sense. That's the end of part 1. Part 2. So, now I'm going to talk about coverability in 2 VASS. Which is something very similar, but I'm going to talk about k-cycle detection instead. So, we just had this theorem earlier, right, that the coverability can be decided in n to 2 to d time. This is the upper bound that I gave you as context. So if I fix d as 2, I'll get a polynomial time algorithm for coverability. So I decided, I opened up a paper and I was like, okay, let's fix d as 2 and see what happens. And we get 320. For the experts here, what's really going on is we actually wrote an algorithm for vector addition systems without states. And in order to simulate states, you add 3 counters. And this simulation also requires quadratic updates. So if you start nesting all this stuff, you'll get an n to like something like 10 times 2 to the 5. That's the kind of upper bound. It's just a constant, don't worry about it, right? This is supposed to be the fine-grained workshop, so I surrender. I genuinely think that you can get this down to actually 20, not 320 if you're a bit more careful in the proof. But still, the upper bound is not that satisfying. But anyway, I'm going to show a lower bound. I just kind of wanted to give a little bit of context on the fact that there's a reasonable polynomial time algorithm for deciding coverability of 2 VASS. And the lower bound will come from k-cycle detection. So the problem is you're given a directed graph, this time directed, it's an important difference. And I'm asked, is there a cycle in the graph of length k? Makes sense. And the k-cycle hypothesis is the following. For every epsilon, right, there is some m, number of edges. And for every m, sorry, there is a k such that there are no m to 2 minus epsilon time algorithms for detecting k-cycles. The moral of this story is that k-cycle really requires quadratic time. And we're going to use this to prove a quadratic lower bound on the time required to decide coverability in 2 VASS with unary encoding. It's the same thing, right? I'm just going to show that for every epsilon there is no n to 2 minus epsilon time algorithm for coverability in 2 VASS. Okay? So I kind of want to make a simplifying assumption because some graphs are kind of ugly, and there's this really, really nice simplification down to k-circle layered graphs. Most of you haven't heard of a k-circle layered graph before. Here's one I made earlier. You partition the vertex set into k parts, and here the directed edges are only allowed to go from vi to vi plus 1, so it goes from v1 to v2, v2 to v3, v3 to v4, etc., and vk back up to v1, otherwise you'd have no cycles and it would be pretty easy. Okay, I hope that makes sense. And so I'm now going to construct an instance of coverability in 2 VASS that will detect k-cycles from graphs of this flavor. So I'm going to split the graph out, I'm going to cut it open, right, and unroll it. So I have v1, v2 all the way down to vk. It's actually exactly the same one as earlier. I spent ages making sure I got the same edges. And then I'll create a copy of v1. I don't want to create this cycle back, but it's a direct copy, like a nodes-to-nodes match. And previously, when I had edges from vk to v1, I'll now have them from vk to the copy of v1. So I've sort of linearized this graph somehow. And I'm going to add just 2 new states, s and t. And I'm going to add some new transitions. So the first transition from s up to the bottom of V1, we'll just add some sufficiently large number to the second counter, precisely the number of nodes in V1. And then as you climb this ladder up V1, you're basically asked to choose a node to begin your cycle, right? I'm going to start at node I in V1, and I'm going to choose the encoding I on counter 1 and n minus I on counter 2. All of the edges that do not have a label have 0 update. These are 0, 0 vectors everywhere. And I'm going to do the same thing on the other side. I'm now going to climb down the ladder. I'm going to subtract one from the first counter, add one to the second, and then take off this large number. And I claim the following. From S, starting with 0, you can get to T with any value if and only if there's a case cycle in the original graph. This is a lot easier than the previous one. And I would have liked to have shown this as the earlier slides, but then the order would have been terrible. It would have been 2 VASS, then D VASS, then 1 VASS. So for phonetics, I went this way. So consider you leave V1 at the ith node and you reappear in the copy of V1 at the jth node, right? Seems like all you can do. The first component forces I to be at least j. Right, because if I had j greater than I and I arrived up here, in order to get down to t, I'd have to go further down my ladder and my first counter would go negative. Right, and I forbid this from happening if you remember the definition slide. The counters cannot go negative. And the other counter is doing the same thing, right? That's why they have the encoding n minus I on the second counter. So the second component is implying that j is at least I. Together, we know that any run from S to T must satisfy that if you left V1 at the ith node, you must reappear at the ith node in the copy of V1. That means you've got a cycle, right? Because I can now rewrap this round and these two nodes match, and so I must have a k-cycle in the original graph. Importantly, this is a linear time reduction. I added 2 states and a few transitions. All these transitions have extremely small weights, something like number of nodes in the graph. This is extremely, extremely simple. And so now if I combine this with the k-cycle hypothesis, then I immediately resolve that under the k-cycle hypothesis, there are no truly subquadratic time algorithms for coverability in 2 VASS, which is really nice. That's the end of part 2. And part 3, as I said earlier, we're going to talk about 1 VASS. And this is why the title of this talk was Precise Analysis. So I'm going to give a very, very basic, almost embarrassing quadratic time algorithm for coverability in 1 VASS. And then I'm going to talk about the combinatorial core behind why coverability in 1 VASS is an AC1, even if you allow binary encoding. And then I'm going to kind of, as it will become clear, we know a lot about the complexity of 1 VASS, but not so much about the fine-grained complexity. So I'm going to throw a problem that I suspect we can solve by the end of the week. Or at least get to the core of it, really understand what's difficult about it. So first, coverability can be decided in quadratic time. So here's a nice observation about 1 VASS, right? So you've got 1 counter, it's really, really important. Everything's really simple when there's only 1 counter. One need not take non-positive cycles. So imagine I have a run, and I take at some point a negative cycle. So I have some node P, I arrive there with counter value, I don't know, 100, and then later I re-arrive at P with counter value 90. I took a negative 10 cycle. I was better off never taking that cycle. I told you earlier about this monotonicity property. If I just bin the cycle out of my run, then I still have a run and I've got a higher counter value. And for coverability, this is great. I just want to reach at least the target. And so this implies the following. When witnessing runs, or when coverability has witnesses, they will be of one of 2 shapes. Either they're a simple path, no cycles at all, or it might take a cycle, so it'll reach a node and it'll have a positive cycle. But as soon as you're able to take this positive cycle once, a little bit like the example on the second slide, you'll be able to take it over and over and over again and morally reach an infinite counter value. And then you can take any simple path you like to the target because I'm no longer scared of negative transition updates, right? I'll always be above 0 because I could have taken the cycle even more if I wanted to. And so this allows you to modify the Bellman-Ford algorithm for shortest paths in integer-weighted graphs. When I gave a practice version of this talk, someone went, what's the Bellman-Ford algorithm? This is very roughly speaking Dijkstra's, but you can handle negative weights. But if you don't know what Dijkstra's is, you can imagine it's BFS, but with weights. But if you don't know what BFS is, good luck getting to your hotel later. But the modification is the following. You flip the edge weights by -1 because Bellman and Ford care to find short paths. And coverability is really about the opposite, right? I kind of want maximum weight paths. So if I flip all of the paths to negative, then you basically get the algorithm with the exception of as you're exploring the graph in this kind of dynamic fashion, At the moment when you take an edge, you should check the non-negativity condition, otherwise you would violate the VASS requirement. That's the only modification. It works and it runs in number of nodes times number of edges time. This is n squared. If you remember n from the orange slide, it was the size of the instant encoder in unary. It was everything, right? The number of nodes, the number of transitions, the one norm of every vector, right? So E is certainly less than n and V is certainly less than n, right? This is pretty crude as fine-grained things go. And on the other side, right, for the complexity of one VASS, recently we've shown that coverability in one VASS can be decided in AC1, even with binary encoded edges. I'm not going to talk about binary encoding much. I think the combinatorial ideas don't require this. And this is pretty much optimal. Let's say optimal to the literature. If you have natural weighted directed graphs and you ask for shortest paths between them, right? It's kind of like coverability when you multiply by -1. The state of the art is that this is an AC1 from Cook in 1985. So if you improve our algorithm for coverability in one VASS, it'd be a bigger deal. I think that people outside of our VASS community would really like to see this. So when working on this, we found a really, really nice combinatorial idea for deciding coverability. I will now show this to you. So an efficient algorithm for coverability in one VASS. You start with the one VASS. Let's call it V0. And then in rounds, I'm going to define new one VASS. So I'm going to consider adding transitions to my VASS. So from V0, I will create V1 by adding these shortcut transitions. To be clear what a shortcut transition is for the sake of this conversation, take two transitions that share a middle node, right? So P to Q, Q to R. And I'm going to consider adding the shortcut P to R, which will have the combined update U plus V. And I'm only going to add it in certain conditions. So the first scenario, suppose U and V are both positive, then I'm just going to add the shortcut, right? I'm not doing anything fancy. I could have clearly gone from P to R without testing the counter. I could just add U plus V, no problem. Similarly, if overall the effect of U plus V is negative, then I could only go from P to R if I had at least the negative update of U and V combined on my counter to begin with. So I'll add the transition. The only case that I can't deal with is if U is negative and V is positive. What's really going on here is that during the first transition, I'm checking I'm at least U, and then I'm adding V onto the counter. So I kind of really need this intermediate step. And so this, I will not add the transition that shortcuts. This is dangerous. And of course, if they're both negative, then I can take it anyway, so I'll add this in the same way that I could handle the positive case. That's it. So I look at all pairs of transitions like this, and I will add the shortcut if it satisfies scenario 1, 2, or 4, and I'll create V1 this way. And then I repeat this. I do this process over and over again, each time adding new transitions to the VASS. And I claim the following. If there was a run for coverability in the original VASS V0, then there will be a run for coverability in the final VASS VK that's just 2 transitions long, which is pretty easy to check coverability at that point. And I needed to repeat this procedure roughly log many times in the number of states. I'm not going to prove this claim, unfortunately. This combinatorial core is beautiful, and just to give a sort of sniff of why AC1, you can do this step in AC0, one of these steps, and you're doing it log many times, which gives you AC1. Just a very quick flavor of this. And so this leads me on to the question that I wanted to share with you that I'm genuinely really interested in, which is what is the fine-grained complexity of coverability in one VASS? There's kind of 2 problems here. One is really asking the right question and getting the right parameterization locked down, and the other is then, well, actually, work that out. So I've just shown you that coverability in one VASS is decidable in AC1, and I've also showed you a fine-grained upper bound of n squared. I say fine-grained in quotes. Maybe we should start parameterizing by the number of states and the number of transitions, and maybe the maximum update. And so, is there a sub-quadratic time algorithm for coverability in one VASS? I think this is a very interesting question. I want to know. And I'm happy to split up n into different terms. I really want to know anything I can. Any lower bounds, any upper bounds, anything. Can we lift these ideas? That's why I showed you the combinatorial ideas. Maybe we've already got the tools to show like a sub-quadratic time algorithm. And maybe there are new ideas. There are these really impressive results from a few years ago about non-linear time algorithms for finding shortest path trees or finding negative cycles. These guys are randomized. I'm even interested in randomized algorithms. I'll take anything. The best non-randomized algorithms for this run in something like root number of nodes times root number of edges times log of the maximum update on the weight of the graph. It's like Goldberg in the 90s, right? Yeah, can we use these? Unfortunately, staring at this was difficult. These are really complicated algorithms that I don't know very well, so I'm happy to meet people who know anything about this and talk more. And one of the steps they do to begin with is they remove negative cycles immediately using some nice randomized searching algorithms. Unfortunately, I don't think we can do this for VASS because of the non-negativity condition on the counter, right? If you have a transition that subtracts 100 and a small cycle before it that gave you +1, right? This is good news for you because you can take the small cycle and move on. I wouldn't want to have removed it to begin with, so I think some of the techniques need to be modified or maybe avoided altogether. So yeah, that's a question that I think most people in this room should be at least slightly interested in. So yeah, thank you. That was the end of part 3. That was the end of part 3. And so to conclude, I've shown you that under the exponential time hypothesis, coverability in DVASS requires n-2 to d time through a nice parameterized reduction from detecting cliques. I then showed you that coverability in 2VASS requires quadratic time through detecting k cycles in directed graphs. And then in the end, I've just shown you the sort of state-of-the-art, the knowledge of coverability in 1VASS, and posed what I believe is an interesting open problem about really what is the fine-grained complexity of coverability in 1VASS. That's everything I have for you today. Thank you for attending my talk.